Welcome to our fluid mechanics lecture with the topic rotating vessel. So in this lecture video, we will solve the 3 sample problems in our handout, and this is the example number 1. An open cylindrical vessel 0.6 meter in diameter and 0.9 meter high is 2/3 full of water. What is the greatest speed in RPM that it can have without spilling any liquid? And B, what speed must it have in order that there may be no liquid within 150 mm of the vertical axis? So this is an open cylindrical vessel with 0.6 meter diameter and it's 0.9 meter high. So let's draw the vessel. So something like this. So it's 0.6 diameter and that is 0.9 meter high. This is 0.6 meter. And it is 2/3 full of water. So contains water up to this level. And that is 2/3. See, so 2/3 of 9, that will be 2 times 9.9, that will be 1.8 divided by 3, that will be 0.6 meter and 0.3 meter. Then for letter A, what is the greatest speed in RPM that it can have without spilling any liquid? So there is rotational axis here. So what angular speed in RPM it can have without spilling any liquid? Therefore, the maximum height that the liquid can reach on this side of the vessel is up to the rim. Okay, so we will have it. We will have a parabola, something like that. And when it comes to liquid with no spilling, we have the height that becomes what is the height here, that is 0.3, is the same here at the depth. Therefore, the total depth of the paraboloid now is h is equal to 0.6 meter. Okay. So we are looking for the angular speed omega. So omega, that will be the angular speed. So in the formula, our formula here is h so h is equal to omega squared r squared over 2g. Our omega here is actually angular speed in rad per second, in radians per second. So that is the angular speed there. So how do we convert rad per second into revolution per minute? So in 1 revolution, so 1 revolution is equal to 2 pi rad. Now in 1 RPM, that is equal to 1 revolution per minute multiplied with 2 pi rad in 1 revolution, and we have here 1 minute per 60 seconds. So cancel revolution, cancel minute, therefore 1 RPM is equal to, that will be pi over 30, and that is rad per second. So we will use this conversion whenever we use the formula here. Okay. So going back to the problem for letter A. So this is for A. H is equal to omega squared r squared over 2g. So given a height of the paraboloid as 0.6, so that is 0.6 equals omega. So what's the omega here? Squared. The radius is 0.3 squared, twice of the gravitational acceleration. So what is now the value for omega? Omega now is equal to square root of 0.6 times 2 times 9.81 all over 0.3 squared. So omega is 11.44 rad per second. So 11.44 rad per second. We will multiply this with 1 RPM. So since we're looking for the angular velocity or angular speed in RPM, so that is 1 RPM all over pi over 30 rad per second. So cancel rad per second. So what is omega? So omega is 11.44 times 30 over pi. So 109.21 RPM. So that is the answer. So what is the greatest speed in RPM that it can have without spilling? So without spilling any liquid, this is the solution. The paraboloid form here has the height equal to the empty space, the height of the empty space times 2. That is the height of the paraboloid. Now for letter B, what speed must it have in order that there may be no liquid within 150 mm of the vertical axis? So we have a different condition for letter B. So for letter B, let's draw again the container. That is our container. And this is our rotational axis. So we have here, omega. So while it's rotating this way, what happens here is that, okay, so given the height of our container, so it is 0.9 meter. So we have here, so the parabola form here is something like this. So it's asking for the angular speed W. So W, in order that there may be no liquid within 150 mm of the vertical axis. So this is the 150 mm, or that is 0.15 meter. This point here from here. Okay. So given that our radius here is 0.3. So how do we solve this? So we have the height up to this point, height of the paraboloid. Let's name this excess here as y, and the total height of the paraboloid as big H. Okay. So what speed must it have in order to have no liquid within 150 mm of the vertical axis? So using the formula y, so y for this part here, the paraboloid, the smaller paraboloid, so y is equal to omega squared r squared, the small r, 2g. The y here is the excess, so y omega squared, the radius of this, that is 0.075 squared all over twice of gravity. So y is equal to 0.075 squared, 2 times 9.81. So that is 867 times 10 raised to the negative 4 omega squared. So we can use this equation for this. Total height for the paraboloid is equal to 0.9 plus y. So total height for the paraboloid is 0.9, and that is equal to, let's equate that. Okay. So h is equal to 0.9 plus y equals omega squared, the radius is 0.3 squared all over twice of gravity. So we have here 0.9 plus 2.867 times 10 raised to negative 4 omega squared is equal to, this is 0.3 squared over 2 times 9.81. So that is 4.587 times 10 raised to negative 3. So 4.587 times 10 raised to negative 3 omega squared. So what is the value for omega now? It is equal to square root of 0.9 all over, that will be equal to 4.587 times 10 raised to negative 3 minus 2.867 times 10 raised to negative 4. So what's now the value for omega? It is 0.9 all over 4.587 times 10 raised to negative 3 minus 2.867 times 10 raised to negative 4. So 14.47. So omega is equal to 14.47 rad per second, and that is 1 RPM over pi over 30 rad per second. Cancel. So omega now is equal to 14.47 times 30 over pi. So 138.18 RPM. So this is the answer for letter B in number 1. So that's for number 1. Or there's another solution here. If you'd like if to be used for checking, there's another solution. Or by squared property of parabola. So what's the squared property of parabola? So what will we do here is that we will have a comparison. So we have here the square of the radius of the bigger parabola over the height of the bigger parabola or paraboloid, okay, divided is equal to the radius squared of the smaller parabola and then the height of the smaller parabola. So again, that is r squared of the bigger divided by each, and then that is equal to small r squared divided by the height. That is y. Okay, so let's do that. That is 0.3 squared all over h is equal to 0.075 squared all over y. So that is 0.3 squared all over 0.9 plus y. That is equal to 0.075 squared all over y. 0.09 square, 0.09y. Yeah, I think it is 0.3 squared. 0.09, correct. That is equal to 0.9 times 0.075 squared. That is 5.062. 5.062625 times 10 raised to negative 3 plus okay, plus what is 0.075 squared. 0.05 is 5.625 times 10 raised to negative 3 y. Okay, so we now have the value for y is equal to 5.0625 times 10 raised to negative 3 divided by 0.09 minus 5.625 times 10 raised to negative 3. So 0.06, y is 0.06 meter. So we now have the value for y. So from the formula, y is equal to omega squared r squared over 2g. We have here 0.06 equals the omega squared. The r of the smaller parabola there is 0.075 squared all over 2 times 9.81. So omega now is equal to square root of 0.06 times 2 times 9.81. Okay. So that is square root of 0.06 times 2 times 9.81 over 0.075 squared. 14.47. 14.47 rad per second. And then we multiply this with 1 RPM divided by pi over 30 rad per second. So cancel rad. So we now have omega is equal to 14.47 times 30 over shift pi. So 138.17 or 18. So 138.18 RPM. So this is the same answer with what we got there from our first solution. So you can use both methods. So that's for number 1. Let's now go to number 2. An open vessel, 0.7 meter in diameter and 1 meter high, is 3/4 filled with oil with specific gravity of 0.8. When it is rotated about its vertical axis with a constant speed of 100 RPM, determine letter A, the depth of liquid at the center of vessel, B, total force on the bottom of the vessel, that is the initial, and then C, maximum force on the cylindrical walls. Okay. So we have here for letter A, depth of liquid at the center of the vessel. So open vessel. So this is so the 1 meter in diameter, and then it's 0.7 meter diameter, then 1 meter high. So 1 meter high, and it is 3/4 filled with oil. So 3/4 filled with oil. So what is 3/4 of 1 meter is 0.75. This 0.75 and this is 0.25. So determine liquid depth at the center of vessel. So we don't know yet. It did not mention whether there is spilling or not. So we cannot just simply assume that this is equal 0.25, 0.25. No, we cannot simply say that, because the problem, it did not mention if there's no spillage. So since given here is the RPM, let's solve for the height of the parabola or paraboloid form by using the formula. So we need to find out what is the height of this parabola. So having get the height of this parabola, let's name it as the height of the parabola, we will be able to find y. Let's name the y as the depth of liquid at the center of vessel. Okay, so let's name that as y. So our h now, the y first, the omega first. Omega is 100 RPM multiplied with pi over 30 rad per second in every 1 RPM. So cancel here. So omega is equal to, so 100 times shift pi over 30. So 10.47 rad per second. So A here, for letter A, will be H is equal to omega squared R squared over 2G. So what will happen here is that we will get the value for H, so that we will get the value for Y. So H is equal to 10.47 squared. The radius is 0.35 squared divided by 2 times 9.81. So H now is equal to 9.85 squared. 2 times 9.81. 0.68. H is 0.68 meter. Therefore, our y now is equal to 1 minus 0.68. So, y is equal to 1 minus 0.68, 0.32. Our y is 0.32 meter. Ayan. There you go. That is for letter A. How about B? Total force on the bottom of the vessel. That is the initial. So what is the total force at the bottom of the cylinder of the vessel? So that is the initial condition. So we know that with this liquid here, it will exert force on the bottom. And what force is that? What kind of force is that? It's the vertical force. That is for letter B. For letter B, we have F at the bottom. That is the weight of the water. That is gamma volume. Now we know that when it comes to the weight of this liquid, given the specific gravity of 0.8, that is equal to 0.8 of 9.81 times the volume. Okay? The volume of the initial condition here, that is pi over 4. The pi over 4, the diameter of 0.7 squared, times the height. So the height here. So that is 0.75. So FB is now equal to 0.8 times 9.81 times pi over 4 times 0.7 squared times 0.75. 2.265 kilonewton. So 2.265 kilonewton. So that's the force on the bottom of the vessel. So that's B. How about C? What is the maximum force on the cylindrical walls given this rotation here? Okay. So let's redraw the container, the open container here, which have a rotational axis here. So what happens is, as the container rotates, the force on the wall looks something like this. So a greater force will go on the bottom. So the question here is, what is F? The force F. So this is, if you look at this portion here, look at this like that, what can you see? What can you see there? So this is 1 meter. So what we can see here is rectangular, and this rectangular here has the dimension 0.7 meter length and then 1 meter height. So the formula for the force F is equal to gamma HCA. Our gamma is 0.8 multiplied with 9.81 our HC is 1 divided by 2, and then our area is 0.7 times 1. So F now is equal to 0.8 times 9.81 times 0.5 times 0.7, that is 2.75 kilonewton. That is force. Okay, so that's for number 2. Let's go to number 3. A hemispherical bowl having a radius of 1 meter is full of water. If the bowl is made to rotate uniformly about the vertical axis at 30 RPM, determine the remaining volume of water in the bowl. So there is a bowl. So let's assume that the bowl is semicircle. So it contains full of water. It's full of water, and then it is made to rotate uniformly about the vertical axis. So this is the rotational axis. So given omega is equal to 30 RPM. So what will happen to our water? It will form a parabola. So what is the value for H? So of course we know the radius here is 1 meter. And then the height of the paraboloid is missing. So omega is equal to 30 RPM times pi over 30 rad per second all over 1 RPM. Cancel RPM, so omega now is equal to pi rad per second. So V remained is equal to V of hemispherical vessel minus V of the paraboloid. So given the formula H is equal to, so where is our H here? Is equal to omega squared R squared over 2G. So H is equal to pi. So pi squared times the radius of 1 squared all over 2 times 9.81. So H is equal to shift pi squared all over 2 times 9.81. 0.503 or 0.5. So volume remained is equal to 1/2 pi r squared. 1/2 pi r squared. So 4/3 pi r squared minus 1/2 pi r squared each. Okay. So this is the volume of the half a circle, and this is the volume of the paraboloid. So that is equal to 1/2, or that is 2/3. 2/3 pi r squared minus 1/2 pi r squared is 1 times the height. The height of the paraboloid there. The height of the paraboloid is 0.5. So volume remained is now equal to 2/3 of pi minus 0.5 times pi times shift pi times 0.5, that is 1.31 cubic meter. So that's for number 3. Okay, so that's all for this video, and the sample problem number 4 and 5 will be on the part 2.